Show that the a sub n term of the sequence 1, 3, 6, 10, 15, 21, is a sub n equals 1/2 times n plus 1. Observe that this sequence 1, 3, 6, 10, 15, 21, is obtained from a sub 1 equals 1. A sub 2 is 1 plus 2, which is 3. A sub 3 is 3 plus 3, which is 6. A sub 4 is 6 plus 4, which is 10. A sub 5 equals 10 plus 5, which is 15. And so we see that to obtain the a sub k plus 1 terms, we would take the previous term a sub k and add k plus 1 to it. For example, a sub 3 is a sub 2 plus 3. K plus 1, where k plus 1 is 3. And it is true because a sub 2 is 3. 3 plus 3 give us a sub 3, which is 6. And this is how we generate this sequence starting with a sub 1 equals 1. To show that a sub n equals 1/2 n times n plus 1 is true for all n terms, we will use mathematical of induction. The principle of mathematical induction states that first, we have to come up with a statement for p sub n. This is the general statement. The statement p sub n is a sub n equals 1/2 n times n plus 1. This is the formula for the n terms of this sequence. To use the principle of mathematical induction, we need to show the base case. The base case is when k equals 1. P of 1 is the statement for the initial term, the first term a sub 1. We check to see if this formula works. A sub 1 is 1/2 times n is now 1, and we replace n with 1. Simplifying this, we have 1/2 times 1 times 2, which is indeed 1, because we see that a sub 1 in the sequence is 1. So the base case is correct. It is true. We then move on to the induction case. With the induction case, we assume that it is true, the statement is true for the case n equals k. When n equals k, the k term is 1/2 times k plus 1. This means to find the k term, we simply plugged in k into this formula, 1/2 k times k plus 1. So we assume that the statement is true for one particular k. We then show that it is true for k plus 1 terms. And to do that, we consider the case when n equals k plus 1. What does this mean? This means this is the formula for a sub k plus 1. But how do we get a sub k plus 1? For this sequence, every time we obtain the next term, we will simply add k plus 1 to it. So for example, in order to get a sub 2, we add 2 to a sub 1. In order to get a sub 5, we add 5 to a sub 4. So we add the subscript to the previous term. The previous term of a sub k plus 1 is a sub k, and we add k plus 1 to it. Remember that we assume that the formula is true for a sub k, where a sub k is 1/2 k times k plus 1 already. So we replace a sub k with this expression. We still have k plus 1, so we bring it down. We will then clean this up or simplify this. This is 1/2 k squared plus 1/2 k plus 1, where we will combine like terms. This is 1/2 k squared plus 3/2 times k plus 1. We then factor out 1/2. We have k squared left plus 3k plus 2, because 1/2 times 2 is 1. We then factor this. This is factorable. 1/2 times k plus 1 times k plus 2. Observe that k times k is k squared. 1k plus 2k is 3k, and 1 times 2 is 3. But to show that the statement is true for the k is k plus 1, which is the input or the subscript times the subscript plus 1 and then divided by 2, we rewrite this as 1/2 times k plus 1 times k plus 1 plus 1. This is the term a sub k plus 1. Since it looks like this form where the input is n, we would take half of the input times the input plus 1. And so if the input is k plus 1, we take half of the input and then multiply the input plus 1. This shows that the case p sub k plus 1 is true because it follows the same format. Since both of the base case and the induction case is true, we conclude that by the principle of mathematical induction, the statement p of n, which is the n term, is 1/2 times n plus 1, is true for all n, not just one particular n, but for all n.